So, hello, in this talk, what I will try to do this is to present some result that deals with soliton in optical fibers. So, this last year we have celebrated the 50th anniversary of the solitons in optical fiber. So there were several things that have been done in that context, and in that talk I will try to show you that soliton are still very important and are still extremely interesting from several point of view. And also in this talk, I will show you that in our region, in Burgundy, at the University of Burgundy in Dijon, we have made several interesting things that deals with solitons and not only in the field of optics. So this talk was provided for the visit of one of the greatest names of the field of solitons, in fibers. This is Professor Govind Agrawal, and I am Christophe. So, Soliton, I will show you how it appears and how it has spread over more than now 3 centuries. So I will go from the 19th century up to results that have been obtained much more recently in the 21st century. And I will not only speak about solitons, I will also discuss some other waves that are called the rock waves. And it will be the last part of this talk. And I will not only focus exclusively on what happens in an optical fiber, I will also show you that this concept of solitons can be found in other fields of physics, and one of the most inspiring fields where everything began is the field of water waves. And through this journey, we will discover many different places, including Burgundy, and we will also see the many great researchers that have significantly contributed to this field. So let's start. And the beginning of this story, it is in the 19th century. So what do we know at the beginning of the 19th century? What is known is that when you have a water wave of small amplitude, then when it propagates, it broadens. This is linked to dispersions. Your components of the wave traverse at different speeds, so it leads to this broadening and the fact that you cannot maintain the shape of your pulse unaffected. Now, if on the contrary you prefer to use a large amplitude wave, what appears is that the wave completely disappears, it is disintegrated, it breaks quickly into several waves of a smaller amplitude. So also when you use a wave of very large amplitude, it cannot be sustained over propagations. And for all this, the modeling is already pretty good. And there are two names that you have to know. One, it is Gabriel Stokes, and the other one is Henri Navier. Their works have led to the Navier-Stokes equations that are the starting point of all the field of hydrodynamics. This is in hydrodynamics the equivalent of the Maxwell equations in the field of electromagnetism. And just a few words about Henri Navier, because he is born in Burgundy, in Dijon. And this is a very famous researcher. He has his name on a building here that you can find this building in Paris, where there are plenty names of great scientists, great French scientists of the 19th century. And among these scientists, there is Navier. Here is just a view of some of the names. And this building in fact, everybody on Earth, I think, knows this building. It is in Paris, and it is the Eiffel Tower. So next time you go to Paris, try to see all the name of the scientists that are put all around the first floor of the Eiffel Tower. And here, if I can just have an additional comment, this is that Gustave Eiffel was also born in Dijon in Burgundy. So then, when does what we now called the soliton appears? So everything starts, in fact, with John Scott Russell, who was familiar with hydrodynamics. He was a naval engineer, so he was building ship. And in 1834, he was riding along a canal and he was following a boat, and this boat stopped abruptly. It generated a high amplitude wave, and John Scott Russell was surprised to see that that was able to maintain its shape and effective along the propagation for several kilometers. So he followed on his horse this wave for several kilometers, and he was extremely surprised to see that kind of behavior, which was completely unusual and unpredictable. So even repeated many times similar observation by varying the shape and varying the parameters. And this has led to him to present the result of what he has called the wave of translation, which is a pretty good name because you have a wave, it propagates just by experiencing a translation. And he presented this to his colleagues, and the feedback was rather negative. So it was not encouraging at all. And the reason of this very cold feedback, it is mainly due to the fact that there was no theory able to explain this kind of behavior. So if it cannot be predicted theoretically, then it should not exist. And among the people that were very strongly against the observation of Russell, there was Gabriel also. Imagine when you have one of the top contributors of your field that is publicly against your finding. Well, this is not a very good sign. And perhaps that everything could have stopped here, but there have been other researchers that were motivated to try to reproduce the early works of Russell. And the second experimental observation of solitons were made in Dijon by two engineers that were also called Henry. So it was Henri Bazin and Henri Darcy. In fact, this is mainly Bazin who made those observations. And they reproduce the observation of just Scott Russell. They made much more experiments in different channels, and they really confirm what Russell have seen. And as you see at the beginning of their work, they completely acknowledge that they want to reproduce the initial work of Russell. That is a work that has to be recognized. And now, if you want just to see an example of this wave of translation, here is one in a channel with a very small depth of water. And here is another video here made in a water tank that we have at the University of Burgundy. And you can see how this typical wave is able to run along the water tank. At the end of the water tank, that is several meters long, it will be reflected at the extremity. You see it, and then it continues its journey. So with all that observation, then it has stimulated some methodical works, and for this, we can analyze the contribution of Boussinet that have made some mathematical modeling of what happens in the experimental conditions. So he has been able, in a very mathematical article, to demonstrate that a wave of transition could, in fact, exist, and he has derived the parameter of such a wave. And when we have a look on at the first sentence of his article, we can see that he based his motivation on the work of Russell and Bazin. But perhaps the best recognized work is the work from two other researchers, Kutterbergs and De Vries, and in a bit shorter article, they derive a simple equation that could take into account the propagation of a wave in the experimental conditions. This is now a very well used equation. This is the Kutterberg-De Vries equation. And they have derived the solution of this equation, which is an hyperbolic secant waveform, and they can also link the various parameters of that wave, such as its amplitude, its velocity, its spatial extent, to the physical parameter, such as the initial amplitude or the depth of the water. So with all the experimental and theoretical contribution at the end of the 19th century, the existence of the wave of translation is now okay for everybody, and it is a process that is well understood. So everything could have stopped here because there was here a good understanding of what happened. So what then? So let's start. And the beginning of this story, at in the first part of the 20th century, there has been no significant research on this topic. And all the new works, they come after World War II because there have been new tools that have become available to make research in physics. It was the computer. So we are after World War II in Los Alamos, and researchers have decided to use the MANIAC computer. So it was one of the greatest computer of the time, but its power now is quite ridiculous if you compare it to any of your smartphone that you use. The researchers that were involved in that research were Fermi, Pasta, and Ulam. And in a pioneering article, they studied a problem that seems at the first stage quite easy. You have 64 particles that are linked by a force. So this is a problem that is often discussed in bachelor's program. And young students are able to see that problem. And they can find the modes that are typical of the propagations when the problem is linear. So when the force between the different particles is linear, such as the Hooke force of a spring. However, in that contribution, what was new and what has been made possible using a computer. This is to replace a purely linear force by a nonlinear force. So in that case, the problem become nonlinear. And you see, in the governing equation of the problem, you have to include some additional term that will make everything much more complex. If you have only a linear problems, then you solve the problems for the modes, and then the modes, there is no exchange of energy between the various modes. Now, if you put some nonlinearity in your system, there will be some exchange of energy between the mode that you define for your system. And it will be a real problem, this exchange of energy, to predict the long-term evolution of your system. And what could be intuitively imagined, this is that with such a mixing, if initially you put your energy in a very simple mode, then due to the interaction, your energy will be spread in all the mode, and you will have a complex behavior, and you will never recover your initial mode. So it was to check this kind of idea that the experimental the numerical experiment was done using the computer. And regarding that work, something should be also mentioned. This is a work achieved by another contributor, which is Marit Singhu, that is only acknowledged at the end of the paper. But when we see why she's acknowledged, we can make out that in fact she has made a great work. She has made all the algorithmic part and everything that deals with maniac. So really, based on our standard nowadays in the 21st century, she really deserves to be part of these problems, and she should have been in the list of authors of the initial work. So here is an illustration of this. We have 64 particles, and initially we send the simplest mode, a sinus wave. And what we see, this is that the wave does not remain a sinus, it becomes more and more complex. We see that here we have a very complex motion, but if we wait for quite a long time, what we will see, they said that after some state of propagation here, you can see that we are retrieving the initial conditions, and then we have a new cycle that begins. So here what we see, this is a kind of recurring motion, and it was completely unexpected. Now it is quite famous, and it is known as the Fermi Pasta Ulam recurrence. But at that time, it really opened a lot of questions. And it has stimulated many research in those nonlinear problems. And among the most famous contribution, we have one in 1965 that have investigated the evolution, once again, of a quite simple wave here, something that is sinusoidal in plasma. So what we see, that the initial wave, it spontaneously breaks, and it leads to the appearance of well-defined structures, so pulses here, that will collide with the other pulses, but they are robust against this collision. We see also that after some while we recover kind of the initial conditions, and we will try then those really well-defined structures that evolve and collide. So this problem, it was studied numerically in plasma. However, the equation that is governing the propagation, you see, this is the Kohlberg-de Vries equations. So we could have the same behavior also for water wave because this is the same physical explanation. And what could also be shown, this is that this equation is linked to the previous problem that was studied if you take some asymptotic limit. So here we have a very interesting behavior that is stress. And what is also interesting, this is that in the title as well as the abstract, this is the first time that the word soliton appear. So before there was this solitary wave or wave of translation, and here the authors have decided to use a name of solitons to try to stress some parallel with the behavior of a particle. And what can also be seen, this is one of the contributors, one from the Bell Lab, a very famous lab, where there have been very fundamental research that were made that have very, very strong impacts in the physics of the 20th century. So here on this illustration, you can see this particle, you can see the trajectory, the fact that they are robust against the collisions. And does it also works with water waves? So we can go back to our water tank, generate a first soliton. The first soliton, as I mentioned earlier, will be reflected at the end of the water tanks, and we launch another solitons so that both will collide. Here is a collision, and after the collision, we see that the soliton are robust. So you see an extremely interesting behavior. And then there have been also progress in the mathematical tools because previous result they were still numerical, and there have been new techniques, new mathematical techniques that have been invented to solve these nonlinear problems. So one of this mathematical method, this is the inverse scattering transform, which is a method that is not simple. It is quite complex, and usually you have to have an extremely good level in mathematics to handle it properly. So it has been used to explore the Kohlberg-de Vries equation, but also some other equations of the field of physics, such as the nonlinear Schrödinger equation. And for this, the name of Vladimir Zakharov is well known. He has made many great contributions. Unfortunately, he died last year. So this new mathematical tool has become very exciting for mathematicians. It has enabled to better understand the fundamental solitons, how it can be linked to other solitonic process. It could be useful to derive the property of collisions, how it can be affected by phase between different pulses, and so on. And this technique is also known as the nonlinear Fourier method. So in the Fourier method, in the Fourier transform, you define mode. So you think your problem in this reciprocal space, and you know that the frequency that are in this reciprocal space, they are linked to cosinus and sinus wave. For the nonlinear Fourier transform, in fact, these are the solitons that are your basis, and you will think your problems in terms of solitons and interactions of solitons. And just a word about Fourier, one of another great scientists of the 19th century. he was also born in Burgundy, not in Dijon, but in Auxerre, which is a town that is not so far away. And with all that progress, it has stimulated many research in other fields. So not only in the field of plasma or water wave, and in Dijon, at the beginning of the 80s, following the works of Michel Rosnoy, there have been quite a lot of studies of solitons in various systems. And Michel Rosnoy was someone that was extremely motivated. He has made an excellent book that deals with solitons in many different systems. He has also been the one that has built the water tank with the video that I've shown you a few minutes before. And he has investigated solitons, for example, in electrical lines. In that case, you just need an oscilloscope to see how the wave could collide. So when you have a line, an electrical line made with nonlinear components, then you can observe such behavior. He has also studied the propagations of solitons in chain of pendulum. So here I have cheated because I have not taken a video from Dijon. Here, this is a video from the University of Le Mans, but the chain of pendulum that they use is very similar to one that was built in our lab in the 80s or 90s. We have several prototypes of them. So you can see was not the only researcher in Dijon at the University of Burgundy that made great contribution. We can also mention his colleague, another Michel Perard, that in his case has been interested in the evolution of soliton in a biological chain such as the DNA. So he also contributed to a great book that is the physics of solitons. I can mention also in the field of mathematics the work of Vladimir Matveyev that has introduced new mathematical techniques to predict and to understand those nonlinear problems. And of course, I can mention the work of Gimilo that has focused on solitons in optical fiber. So with all those examples, you begin to see that solitons is quite universal. You can find them in water waves, you can find them in plasma, you can find them in electrical lines, you can find them in DNA, you can find them in magnetic materials also, as well as in your body with some interpretations of your heart pulsation in terms of solitons. You can find them all around a stadium with a hola. You can find them in weather here with some clouds, and you can find them in planetology. So as soon as you may think that you have some nonlinearity, then you may imagine that there could be some solitonic effect that may exist. So let's start. And the beginning of this story. And so now we arrive in 1973 with soliton that is applied to a new field, which is the field of optical telecommunications and optical fiber. So what do we need if we want to observe some optical solitons? The first things that we need, this is to have a medium of propagation when the light will be guided. It will be the optical fiber, and it has been put into light in 1966 by Charles Cow. And the other thing that you need, this is a wave that is powerful enough to get some nonlinearity, and for that, what will be useful, it is lasers. And lasers, it has been invented in 1960. Both of these have been awarded the Nobel Prize, and in fact, in the case of the lasers, there have been plenty of Nobel Prizes that have been given to this field. So, using light to generate an optical soliton in the fiber, it was proposed by two researchers, Akira Hasegawa and Frank Tappert, in 1973. So last year it was the 50th birthday of this proposition. The article, what we can see, this is that it comes from an industrial lab. Once again, this is from the Bell Labs. And this work is in fact quite short, only 2 pages if you exclude the references, but there are plenty of things in this very short article. So the first things that you can find, this is a governing equation that is able to take into account both dispersion and nonlinearity. So when you have a pulse that propagates inside a single mode optical fiber, then the evolution of its temporal profile is subjected to the dispersion. So this is what broadens the temporal profile of the pulse. So this is a linear effect that which can take here into account with this term. The second effect that was also present in fibers, this is Kerr nonlinearity. So this is the second term in these differential equations. So in 1973, this knowledge of the nonlinearity was very recent because it was only a few years ago that Ashkin has worked on this topic to show that there could be some nonlinearity. So you see, the equation that governs propagation is quite simple. It is called the nonlinear Schrödinger equations, and this is an equation that is known in other fields of physics. So with that, you can take some of the tools that have been developed around this equation. I have mentioned the nonlinear Fourier transform or inverse scattering transform, and it tells you that you can expect to have solitons. Here I just speak about the temporal evolution of the pulse of light because we are considering single mode fiber, so the spatial profile of light does not evolve. There could be spatial solitons, but this is a different subject that I will not discuss in this lecture. So if you want to better understand how these two terms change the property of your pulse, you can take the dispersion and the nonlinearity separately. If you only consider the dispersion, so without any nonlinearity, this is possible if, for example, you have a very low power pulse. In that case, the system is linear. Your spectrum is not affected by the dispersion, but each spectral component will experience a delay that is different, and that leads to a broadening of your pulse. So your pulse will broaden, and at each time, you may have a frequency that is different. So this is what is called a chirp. So you will have a distribution of the instantaneous frequency that will depend on the initial shape. So this is the effect of dispersion. It changes your temporal intensity profile. Now, if we consider the nonlinearity alone, so without any dispersions, in that case, the problem, you can solve it in the temporal domain. And what you have, this is that your temporal intensity profile does not change. But at each time, you will have, once again, a different frequency. So there will be, once again, a chirp that will appear. And you see here that the chirp can be quite complex. In fact, it can be shown that this profile depends on the temporal gradients of your intensity profile. And if you increase the power, then you will also increase your chirp. And as you change the distribution of the instantaneous frequency, you create new frequency that may interfere, and it will lead to a broadening of your spectrum. So you see, in the most general case, you may have both broadening in the temporal and in the spectral domain. So your pulse will be really affected by the two effects when it will propagate, and you may easily imagine the nightmare that it could be for optical telecommunication, where the dream this is to have a pulse that is an ideal bit of information, so a pulse that can remain unaffected upon all the propagation. Now, what happens when you have a soliton? A soliton, this is a very specific pulse shape. So this is an hyperbolic secant waveform with the good power. So first, regarding dispersion, here, if I consider the propagation over a very small distance of propagation, the consequences of dispersion, it will be to include a chirp in the temporal domain, and you can see this the shape of a chirp that it will lead to. Now, regarding the nonlinearity, you see that the shape that is linked to the nonlinear effect regarding the chirp is very similar to the one that is induced by dispersion. And if you take the right power, then the two may have the same amplitude and they will be able to exactly compensate. So if over a very short distance of propagation you had dispersion and nonlinearity, what you get, this is a stationary wave, you will have a perfect compensation of dispersion and nonlinearity. Your wave will be able to propagate without any changes. So here I have discussed things over a very short distance, and the idea of considering only short distance of propagation. In fact, this is at the heart of an algorithm, a numerical algorithm, that is the standard algorithm that we use. It is an algorithm that has been developed by Frank Taper, and its first use was in this pioneering article of 1973. So what else was present in this article? There was the fundamental soliton, as I have tried to make you understand how this soliton may appear from a perfect balance between dispersion and nonlinearity. And if this balance is only periodical, this is the case when you have a higher power that is launched in your fiber, then what you will get is a higher order solitons when you will recover the initial shape of your pulse, but only at a periodic distance of propagations. And in an article that is tightly connected to the initial article, tapered on the Agrawal, consider the case of normal dispersion, and in that case, this is another kind of soliton that appear. This is, in that case, all of light over a continuous background. So all that was proposed in 1973, and the experimental demonstration was made only 7 years later in that article published in Physical Review Letters. It was the first demonstration of an optical soliton in a single mode fiber. So an ultra-short pulse was initially launched into the fiber, and after several hundreds of meters of propagations, the pulse is at the output identical to the initial pulse. Here, temporal duration of this pulse was short, a few picoseconds only, and at the time, of course, it was a great demonstration. Once again, we can see that this work was achieved in an industrial laboratory. It really stressed that it was really interesting for the industry to have this kind of very powerful pulsables to propagate without any deformation. And if we now have a closer look to this experimental result, we can see that the fundamental soliton is the same as the input pulses, and when we increase the power, what we can see, this is that we retrieve the property of a higher soliton that is not identical to the pulse that is initially launched, and that experience some temporal compression. So this could be very interesting if you want to generate short substructures. You want to get a pulse narrower in the temporal regime, so soliton in that case can be very useful. And if you further increase your power, then you can also have a splitting of the pulse into two substructures. So on this slide, we have also compared the numerical simulation were done by Bertrand Kibler, the experimental result with numerical simulation based on the nonlinear Schrödinger equation, and we can see that there is a good agreement between the numerics and the experimental result. So it confirms the validity of this differential equation to model propagation in a single mode fiber. And if you want to know more about propagation in an optical fiber, all the additional terms that may influence this propagation, as well as soliton and their application, the Bible of this field, this is the book of Govind Agrawal, Nonlinear Fiber Optics, that was first published in 1989, and now this is the edition number 6. This book is not the only book from Professor Agrawal. He also published many other books. And you see, if I make a search in the database on the keyword soliton and fibers and waveguide, I can find more than 20,000 articles, which is huge. And there have been also plenty of books that have been devoted to this subject. So it has been a huge subject of research that has stimulated many works in many different institutions. And it has also led to some startups. So two startups were launched with the idea to benefit from optical soliton. One was French, it was RGT, and the other one was English, based on the works of Aston University. And in fact, unfortunately, both of these companies were launched around the year 2000. They had great success when they have been sold, but then they crashed due to the explosion of the internet bubble. So, was it the end of the story for Solitons in fiber with the crash of this industrial company and with at the end the conclusion that perhaps Soliton will not be so useful for optical telecommunication? Does it lead to a clear step of the research? This is what I will try to discuss in the following of my talk. So let's start. And the beginning of this story and what has happened after 2000. So first, to reply to the previous questions, if I have a look to the database, so the database that I use, this is Web of Science, which is quite quite an important database. This is one of the referents in the field of science and physics. And I have tried to see the number of publications that deal with soliton fiber and optical waveguide according to the year of publications. And what we can see, this is that after year 2000, there is a small drop in the number of works that have been published, but nothing extremely significant. But after that, we see that there is a huge increase in the number of work that are published in the field. So here the conclusion this is that the interest in optical soliton is far from being over, and on the contrary, there are more and more works that deal with this subject that become available in the literature. Another way to see that, this is to have a look at the number of citations of the Bible. As I told you before, so the book of Govind Agrawal. Here I have used a Google Scholar database, and what we see, this is that each year the number of citations of this work is above 1,200 citations per year, which is absolutely huge. So it confirms that this subject is still motivating many people. So where are these people from? So here, based on the Web of Science database, I have tried to rank the different countries that are involved in these publications. So we find that China is the most contributing country, but this is a conclusion that we may have for many different fields. We see that USA and Russia are also deeply involved, and Russia has developed a very strong mathematical skill around this subject. And here, the good surprise is that France come as the fourth country in the subject. So here, France is far from being ridiculous. And if I have a look at the institution that have published the most in the domain, the institution that is the most visible, this is the Centre National de la Recherche Scientifique, the CNRS, which is a French institution. And we can also see the very good ranking of the University of Burgundy, so in France, so in Dijon, in Burgundy. So we are quite proud of that. And as a way to see how important a subject could have been in the field, this is to have a look at the various researchers that were involved in the topic. So here I had a look to the ranking that is published once or twice a year, made by researchers from Stanford University based on Elsevier database. So in that ranking, they are looking at the 2% of the best scientists in the field. So one thing before showing this ranking, this is that when you deal with such ranking, you have to be very careful because this ranking depends on the number of citations of the various paper. They could be potentially biased, so be careful and do not overinterpret the result. But what we may see, this is that you see here in green, I have highlighted the researchers that have been involved at one stage of their career in the physics of solitons. And you may see here that over 26 best researchers in the field of optics, 11 have worked for several years dealing with solitons. And you may see that Professor Agrawal is among the top 10 of the researchers. Now we can just have a look also at this ranking, but restricted to France. So here, this is more for French students. And what we may notice, this is that once again, the number of researchers in optics involved with solitons in fiber is quite significant. And in green, what I have stressed also in the second column, this is the researcher that has linked to the University of Burgundy, or more specifically to our laboratory, which is the Laboratoire Carnot Interdisciplinaire de Bourgogne. So you may see that 5 over the 25 best researchers identified in this ranking with all the care that we should keep when it deals with such ranking are linked to our laboratory. So once again, we can be quite proud of this. And on top of that, we should mention that 2 other researchers are in the closest university, the University of Franche-Comté. This is John Dudley and Laurent Larger. So if you want to make some optics in the field of soliton in optical fiber, it could be a really good idea to come to Bourgogne-Franche-Comté. And to finish with this ranking, here I have tried to have a look to the 15 most cited articles that deal with soliton fiber optical waveguide. And what you can see, this is that, of course, you have the works of Tappert and Agrawal, the one, the article from Molyneux, Stollen, and Gordon, and you can find 2 contributions when ICB Lab is involved, as well as 2 contributions where our colleague John Dudley from University of Franche-Comté is involved. And what you may also notice, this is the term of rogue wave, and this will be the last part of my talk. And you can also see that if you want some highly cited works to make a review paper will lead to significant number of citations. And now, if I ask the question to ChatGPT to tell me what are the 5 most significant articles in the field, here is his answer. Of course, I agree with the first 2 works that he mentioned, so article of Agrawal, Modern Hour, and the book of Govind Agrawal. Do not fully agree for the last 2 contributions. So more general comments: when you use ChatGPT, be extremely cautious, because some part of the answer will be true, some other part may be much more disputable. And always try to make bibliographic work by yourself. Do not rely on ChatGPT and do not use ChatGPT to build your report because the reviewer will clearly see it quite quickly, and the feeling that you will have will be very negative, I can tell you. So now, why is there such an interest in optical soliton? This is because there are still many directions that are open. So here I've taken this figure from a review paper published in Nature Photonics last year. And what we can see this is that there are still open direction on fundamental aspects. So regarding new open questions, everything is not yet known about the solution of the nonlinear Schrödinger equation or its variants when we had some additional effect because you can consider a multimode fiber now, you can consider plenty of other kind of couplings that will enable you to see another physics or another interactions. But also, what has made the success of the solitons? This is all the potential field of application that they may lead to. You may believe initially that solitons will only be restricted to communications, but it's only a small part that is not in fact so significant. So we have tried in an article published in Optics and Photonic News last year to see what could be the field that where you may find soliton in fiber, and you see you have the source of light. So solitons in optical fibers. This is a new way to produce a new kind of optical sources. So it can be using, for example, new kind of fibers, such as this photonic crystal fiber, where you can tailor the propagation of the soliton and you can change its wavelength. It can be also hollow-core fiber. Here, a great example where pulses with duration below the femtosecond time scale have been obtained with peak power that are huge. There could be also brand new sources, such as supercontinuum sources. Here, it was using new kind of material, chalcogenide glasses, and launching light into this fiber. You have a plethora of nonlinear effects that will lead to a very significant broadening, and at the output, you have a continuous spectrum starting below 2 microns and expanding up to 18 microns. So here it was at the time a kind of world record. It was made in Dijon. This is still, I think, the world record. And to see the different trends that we have in the last decades, we can once again use databases. So from the next result, what I have done is to extract from the databases the article published in the last decades, including the reference. And then I use a software, which is SiteSpace, which is free available, and this software makes connection between the different articles according to the citation that they contain. And with these tools, what we can see is that we have several clusters. We have one that deals with theoretical work mainly, where typically this is some new terms that are added to the nonlinear Schrödinger equations. So some additional complexity that is added, and then there is theoretical or mathematical discussion regarding the property of the wave that you may have. Another cluster deals with work waves. It will be the last part of this lecture. And the other cluster that is split into deals with fiber lasers. So here, this is another view of these clusters. So regarding the last cluster of fiber lasers, you may see that there are two parts. One, in fact, deals with subturable absorber because they have been heavily investigated to provide some new way to have fiber laser that provide some very nice solitons. But here for this cluster, this is more material science. The physics is more in the other cluster that works with dissipative solitons. And we see that it can be linked also with the field of work wave. And what is nice with the software that I have used here, SciSpace, this is also that it tries to propose the name of the most significant author of the author that has been the mostly reference for this cluster. So in the field of work wave, this is Govind Agrawal, because I think that all the paper cite his book as a starting point. And regarding the field of dissipative solitons, this is Philippe Grelu. So as I said, work wave, wait some minutes before knowing what it is. For the fields of dissipative solitons, this is an extent of the concepts of solitons when you add some losses as well as some gain. And in Dijon, we are a few to work on this topic, and the leader of this subject, this is Philippe Grelu. So now, what else are we doing in our team? So the team is quite big. You see here all the permanent researchers working on the subject. It has been initially created in 1998 by Guimilo, that has been at the head of the team for 23 years now. This is Bertrand Kibler. And the team has changed its name. Initially, it was Soliton Laser and Optical Communications. Now we have lost the optical communication term because this is not so significant anymore, and it has become soliton lasers, fibers, and mid-infrared photonics. So what are we working on? Because in the past slide, I've mainly based my discussion on what have been published. So this is more the past. Now, what are our undergoing research dealing with? So I have tried to summarize our topic. One deals with cavity and combs, and so this is a new kind of way to have spectral property that could be interesting for sensing, that can be also lead to a new physics of the solitons, of the cavity solitons. And one possible direction is to, instead of doing this in fiber with segment of a few meters or a few tens or hundreds of meters, to do it on the ship scale. So we are trying to investigate this. Another direction, this is multimode fiber optics. So this is a subject on which we have been working quite extensively in the last year. And for this, we can use some very advanced methods where we can draw a parallel between what happened in this multimode fiber and the process of thermalization, condensation, for example, when you consider statistical physics. So there could be a very interesting analogy. As you may have understood by the name of the team, the field of mid-infrared of new material is something also where many people are involved. And finally, in my case, my main topic now has become the use of new tools in the field, for example, of machine learning. So it opens new directions. It does not describe new physics, but it can provide now new angles to interpret some phenomena. So let's start. And the beginning of this story. So I now arrive to the last part of my talk, and as I have promised you several times, it will deal with a new kind of wave, which are the rock waves. So what is a rock wave? A rock wave, this is initially a wave that you can observe in the ocean. And this is a wave that is extremely powerful, so a very large amplitude that is very rare and that has the property to appear from nowhere and then disappear without leaving any trace. So there have been many reports, oral reports, that has been assessed by, for example, you see the shape that have been heavily affected by such wave. But there were not many scientific measurements of this wave. And it was quite hard to put numbers on top of that. We just had to trust the report of the sailors. But everything changed following some measurement made at the seashore. And here, this is the record that is now known as a Dropner wave. So it was at the first day of 1995, and we can see how huge this wave can be with an amplitude from the bottom to the top of the wave that is more than 25 meters. And how does this wave appear? So here there have been several attempts to explain them, but one solution that we have found quite interesting, it was the prototype proposed mathematically by Owen Peregrine in 1983, so 40 years last year. And the expression of this wave, you see, is quite simple. This is a rational soliton. And here is, when we draw the solution, what it looks like. You see, initially you have something flat, and then the energy gets concentrated, it increases, and then it drops. So here, what is interesting, this is that we have this very strong wave that comes from nowhere and disappear then without leaving a trace. And here it could fit the observation of the rock wave. However, here the solution has only been proposed mathematically. So there was no one that have tried to observe it in any physical system. This is what we have tried to do. So it was our challenge in 2010. We wanted to be the first to demonstrate a rock wave in a lab. So here we didn't have to go in the ascent. We did not have to be at the bad place at the bad time to measure several meters high wave. So we can be in a warm lab. We have a laser. So we put on top of this laser a small perturbation. We launch light into the fiber and we detect what we have at the output. So we can do that using devices from telecommunication. So this is something that we did in 2010 in collaboration with Jean Dudley from the University of Franche-Comté. I previously mentioned his name, as well as Nel Akhmediev, a mathematical researcher from the University of Adelaide, so from Australia. And here is what we observe. We can see that initially we have just a small perturbation, and then this perturbation grows. It reaches its maximum, and after that, it collapses. So we have the property expected for the work wave. It is interesting to go deeper into the details. We see here how the energy is focused, and we can compare this, so this experimental result with the result obtained from numerical simulation of the nonlinear Schrödinger equation, and the agreement is really good. And now, if we try to compare the temporal profile that we have at the point of maximum focusing, we see that the experimental results are very well fitted by the property of a peregrine soliton. And here we have not tried to adjust the parameter we used, neither in the numerical simulations nor in the mathematical fit. So we can be quite confident with the fact that we have generated for the first time a prototype of the peregrine soliton. So then it has stimulated interest in many other research fields, and 1 year later, peregrine soliton was demonstrated in hydrodynamics in a water tank. It was also demonstrated in the field of plasma. It took more time to see it in quantum physics. It has been published only in 2024, and people have believed to also have seen some rock waves, some peregrine rock waves in the field of economy. Here, they were observing the evolution of the debt of the of Italy during the crisis. But now, if we want to better understand where this rock wave come from, we can remember that in the ascent there can be some patterns that emerge spontaneously and lead to some strong waves. This is known as the Bazin instability, and there is a kind of similar process in the field of optical fiber. This is called, in that case, the modulation instability, and it has been published initially by Akira Hasegawa, so a name that you are now familiar with. And what is it? So let's say that you send in your fiber a continuous wave that is highly powerful. After some propagation, the wave will not remain continuous at all. It will split into plenty of sub-pulses that are very short, and one of the sub-pulses will be of high amplitude. Here, it could be a work wave. So there is for sure a connection between this modulation instability and the work wave, the peregrine solitons. It can be interesting to have a look at the process in the spectral domain, and we can see that one of its characteristics, this is the growth of sidebands. So some part of the spectrum get amplified and the process get cascaded. Mm, There is not a single type of modulation instability. There could be the various process that leads to this process of modulation instability. And here, this is just another example that has been proposed by Professor Agrawal. And you see, there are many other processes that may lead, in the case of a continuous wave, to a splitting and to the generation of substructures in an optical continuous wave. Now, come back to our experiment dealing with peregrine soliton. What can we see in the spectral domain? We'll see that we have sidebands that emerge, and then everything gets cascaded. And what we can also see, this is that then the process gets reversed, and most of the energy is focused back to the initial component. We can see it also on this illustration. Here, this is the analytical solution. And that may remind you something. We are back to the problem of Fermi, Pasta, Ulam, and Singu. And to further explore this, we have built in the last thesis that has been defended by Anastasia Shevaleva, a dedicated setup that was able to be in a perfect framework and to see this periodical exchange of energy between the sidebands that could be interpreted with very simple model. We were also involved for the understanding of all that, some neural networks. And you see that everything can be connected. And this process of Fermi-Pasta-Ulam single problem, that can also be seen in water tank here. This is some result obtained in a collaboration that involved Bertrand Kibler from our team. So let's start. And the beginning of this story. So it is now time to conclude. Soliton have been studied for more than 200 years now. Well, not exactly, a bit less, sorry, than 200 years. First in water channels, then in optical fiber, in plasma, in many, many different fields. And something that is very nice, very smart, this is the universality of this concept. What we can see, this is that the understanding at each time being pushed by new experimental or theoretical tools. I think that there are new opportunities with the use of artificial intelligence. And what also I find extremely interesting, this is that with Soliton, you can mix some very fundamental concept with some very practical application. And for all those reasons, I firmly believe that the story of Solitons is far from being over. So thank you for your time, for your listening, and I hope that these lectures and Soliton and optical fiber may have convinced you that this is a great subject that is worthy of further investigation. Thank you. So let's start. And the beginning of this story